In this video, we're going to discuss the autoionization of water. And this is a really critical reaction in our understanding of acids and bases, because it turns out that water in and of itself actually does ionize to form a small concentration of hydroxide and hydronium ions, even at neutral, even in a neutral solution. So even without putting an acid or base in, we get a small concentration of hydroxide and a small concentration of hydronium. And this is in equilibrium. So the two water molecules are interacting with each other, and one donates a proton to the other, making hydronium and hydroxide. So this is an example of an acid-base reaction. It turns out, though, that in this case, the water is the acid and it is the base. So one water molecule plays the role of the acid and another water molecule plays the role of the base. And then on the other side, we form the hydronium, which is an acid, and the hydroxide, which is a base. So this autoionization of water can be thought of as an equilibrium, and we can assign it an equilibrium constant, which we call Kw. And if you remember, when we write an equilibrium expression, it's going to be equivalent to the concentration of OH minus times the concentration of H3O plus. And we leave out the water because the water is a liquid and its concentration doesn't change, so it gets left out. And so the value for Kw is 1.0 times 10 to the minus 14th at 25 degrees Celsius. So that is the value for Kw, and that's the value that we tend to work with Kw. So now the question is can we address what the concentration of OH minus and H3O plus is at equilibrium? And we can. And basically what we can do is construct a small ice table, and from the ice table we can come up with values for the equilibrium concentrations, and then solve this equilibrium equation for those values. And so if we set up our ice table, initially, we're going to have 0 molar and 0 molar H3O plus, right? So if we started out with a solution of pure water, and it hadn't had a chance to ionize yet, we're not going to have any of these compounds. Now, because of the stoichiometry, we're going to get one equivalent of hydroxide and one equivalent of hydronium, and I get that from the stoichiometry. And so we're going to wind up with X and X. And so if we plug those in to our Kw expression, where we have X times X is equal to 1.0 times 10 to the minus 14th. We can solve this by taking the square root of this side and taking the square root of this side, and you have to just recognize that that is x squared. So what we get is we get a value of x equal to 1.0 times 10 to the minus 7th molar. And so it turns out that the concentration of hydroxide is equal to the concentration of hydronium, which is equal to 1.0 times 10 to the minus 7th molar. And this is when there's no acid or base present. So this is what we call a neutral solution. So there's no extra acid or base present in the solution. Now, what ends up happening is when we add an acid or base to this solution, we perturb this balance of the hydroxide and hydronium. So when something is neutral, and what we're going to actually find out in the next video, is that this 1 times 10 to the minus 7th is kind of an important thing. When you convert this to a pH, and we'll talk about how to do that in the next video, you get a pH equal to 7. And so we all know that a pH equal to 7 is neutral solution. It's neither acid or base. And the reason for that is because at a pH of 7, the concentration of hydroxide is equivalent to the concentration of hydronium. So there's no excess acidic or basic components, and therefore they're equivalent, and so therefore we call it neutral. Now let's look at what happens when we perturb that neutrality, that balance. Okay, so let's ask ourselves the question, what is the concentration of H3O plus in a solution where we have a concentration of hydroxide that is equal to 2.5 times 10 to the minus 5 molar? So in this case, we have our Kw expression where we have our concentration of H3O plus times our concentration of OH minus is equal to 1.0 times 10 to the minus 14. We can use this expression to plug this in and get a value for the concentration of H3O plus. Now, if our solution has a concentration of OH minus, we can plug this in directly as our concentration. So that it can be thought of as an equilibrium concentration. What we're going to see in the next chapter is that this actually gets a little bit nuanced, a little bit more nuanced. But for this level of discussion, when we're working with strong acids and bases, which this would be the case of, we can just think of this concentration of hydroxide, which it is. We're saying the concentration of hydroxide in the solution is 2.5 times 10 to the minus 5 molar. We can directly calculate for the concentration of H3O plus. And so what we would do is we would just plug in that concentration of 2.5 times 10 to the minus 5 molar. is equal to 1 times 10 to the minus 14. And what we're going to get from that is we're going to get a concentration of 4.0 times 10 to the minus 10 molar. And so what we notice is something interesting happens. So in this case, when we increase the concentration of hydroxide and we raise it up from its neutral concentration of 1 times 10 to the minus 7. So you see here, we went from 1 times 10 to the minus 7 at neutral to 2.5 times 10 to the minus 5. What we notice is that that results in a corresponding decrease in the concentration of H3O+. We increase the concentration of OH minus, and we see that the concentration of H3O+ goes down to 4.0 times 10 to the minus 10. So we can describe these conditions as either acidic or basic, depending on which one is higher than the other, which concentration is higher than the other. So in neutral solution, we said that the concentration of H3O+ is equal to the concentration of OH minus, and this is all equal to 1.0 times 10 to the minus 7. So in basic solution, which is what we have above, we have a predominance of base. And so we get a condition where we have more OH minus than we would have at, we would have a concentration of OH minus more than we would have in neutral solution. So in this case, the concentration of OH minus would become larger than the concentration of H3O+. And we have basically our balance gets knocked off, and now we have more base than we have acid. And in the case of an acidic solution, we have more H3O+. And so this would be the case where our H3O+ concentration becomes greater than our OH minus concentration. And remember, when one goes up, the other must go down. That is because of our Kw expression. They're inversely proportional to each other based on the Kw expression. So what's interesting is that we can start to think about this in terms of what would happen if we were to add a strong acid or a strong base. So that's going to be one of the things we talk about after the next video. So the next video, we're going to just recast some of this in terms of what we call pH.